Hello! What I'm going to do for you today is a couple of the static electricity problems. They are the sea level, the easier objectives. So I'm going to do one where we touch different spheres together and what kind of ending charge do we have. I'll do another one where we have different points and we want to find the total force on a particular point charge. And I will do some more general stuff too. So the one I want to start with is just if I've got three identical spheres. So I'm going to have A, B, and C, three identical metal spheres, and we're going to have A with a minus 14 charge, B with a minus 8 charge, and C with a plus 7 charge. And then I want to touch B and C together and then pull them away from each other. So if I pull these two together, what's going to happen to the charges on them? Okay, so I've got the negative 8 and the plus 7. If I think about this, I can do it two different ways. The negative 8, okay, so we have 8 extra negative charges. Those are trying to get away from each other. So they're going to want to spread out as far as they can. So I'm going to have 4 on this and 4 on this. And then with the negatives, the plus 7, I'm going to end up with, okay, yes, and yes, we can have a half charge. This is really coulombs of charge, not individual charges. So I can have plus 7, they're going to split up, so I'm going to have 3.5 here, pluses, 3.5 pluses here. They want to spread out equally. And I can say, okay, so what's left on each individual charge? We'll have 4 negatives and 3.5 positives. That means each of B and C are going to end up with half of a negative. I'm going to keep it in fractions. I didn't do anything with A, so A stays at minus 14. Now the other way you can think about it, if you don't want to think about the individual positives and negatives, is you can say, well, how much total charge is there? Plus 7, minus 8. So that gives me a total of minus 1. So the total amount of charge on these two spheres together is minus 1. When I touch them together, they're going to spread that charge out equally. And so minus 1 divided equally across the two spheres, half each. That's the other way to do it. So now I have A at 14 minus, and B and C each at negative 1/2. Now I'm going to touch A and B together and then separate them. Again, what's going to happen? Oh, these numbers are awful, aren't they? Minus 14 and minus 1/2. So the total there is minus 14.5. Okay? So that minus 14.5 is going to get spread out evenly to both of the spheres. So I'm just going to divide it by 2. That's going to give me minus 7.25, right? Did I do this right? I feel like I'm doing something wrong here. So minus 14. So this is a negative 1. So negative 1/2 minus 14.5, negative 7.25. Got it. Okay, so A ends up with negative 7.25. B ends up with negative 7.25. C ends up with negative 1/2. So negative 0.5. And this is my final state after I take the starting conditions, touch B and C together, separate them, touch A and B together, separate them. Here's where we end up. And the nice thing is you can double check your math on this. What is the total charge before and after we've done all these different machinations? Because we cannot destroy or create charge, which means that whatever total charge we had at the beginning and whatever total charge we have at the end better be the same. So if I add this up, so negative 14 and a negative 8, that gives me minus 22. Minus 22 plus 7 is minus 13, if I'm doing that right. Yep, minus 14. No, how about minus 15? I can do math. Here, what's the total charge I'm ending up with? All right, so my total charge, 7 and 7 is 14. 14, half and a half, so we've got 14.5, and add another half, we end up with minus 15. Minus 15, minus 15, got it. So that's how you do the basic conservation of charge, where you're touching different things, separating, touching two other things, separating them. And remember that you can double check your math by figuring out the total charge beforehand and after, and if they're different, you know you made a math mistake. So that's the first of the types of problems that you're going to have on the static electricity. And you can do whatever mix of things, you know, you could try it with A and B first and then doing A and C, and there's all sorts of different number combinations. There's more than you could ever want to do, so if you want some practice, just get together with a friend and trade different problems with each other. You should be able to end up with the same number both times. So that's the first one. Next type of problem I want to do is another, a little wet there still, is the Coulomb's law problem. All right. Oh, well, there we go. Okay. So a Coulomb's law problem where we have 3 charges and we want to know what the net force would be on a 4th charge. So what we typically will have for these problems, A, B, C, and D, I'll give you 4 different situations. And it'll look something like this, where there'll be 3 charges, maybe pluses, maybe minuses, and then a dot. Negative, plus, dot, plus, dot, plus, minus, plus, negative, dot, negative, negative. Okay, so this is what the setup looks like. And what I'm going to ask you to do is rank these 4 situations based on the net force on a positive charge at the dot. So I'm going to pretend that there's a little positive charge here. For each of these cases, a tiny little positive. Pretend there's a tiny little positive. And I want to know in which of these 4 cases is the net force, the total force, on this going to be the biggest? In which case is it going to be the smallest? So this is a conceptual question about Coulomb's law. And Coulomb's law, KQ1, the force between 2 charged objects, KQ1, Q2, over R squared, absolute value. Remember that this is just the size of the force. It doesn't tell us anything about direction. So here's our Coulomb's law. We want to apply it here. Okay, so what I'm going to do, I'll do A in big gory detail, and then others we can do a little bit more quickly. So here's A. And we're going to put a tiny little positive charge right here. What is that positive going to feel from the other 3 charges? And now I don't care what this does to other things. I don't care what this feels. I don't care what this one feels. I don't care what these 2 do to each other. You are this positive, and what do you feel? That's what I care about. So let's take this one. And it's a negative charge, and I'm positive. Opposites, we're going to be attracted to each other. So I'm going to be attracted to the right with, and what I'm going to just say is a size 1. I don't know what the actual numbers are, but this is a size 1 force. So I have a charge here at a certain distance. I'm going to call that size 1. So now what do I feel? I'm the tiny positive from this positive. Well, we have like charges. We're going to repel each other. So now I have another force pushing me this way, and it's at the same distance, and it's the same size charge, so this is another size 1 force, same direction. Then I have another positive here, and it doesn't matter that there's this positive in between. You can ignore this thing. So you can just deal with this positive on me. I'm positive. That positive, we're going to repel, and it's twice as far away. Here's the tricky part that a lot of people don't get right. R squared, the distance is squared in the Coulomb's law equation. So we've gone over this a couple times. I just want to remind you, what does that mean? If I double the distance, the force doesn't go down by 1 over 2. It's going to go down by 1 over 2 squared. So if I've doubled the distance, it goes down by 1 over 2 squared, which is 1/4. So this gives me a size 1 force to the right. That's a size 1 force to the right. That's a size 1/4 force to the right. So the total force from situation A, so the total force that this little positive would feel, is 2 1/4 to the right. So that's a general process you're going to take for doing this. So let's do this a little more quickly for B, C, and D. So I'm positive, what do I feel? Okay, this positive is going to make me want to go that way. So I'm going to have a size 1 force repelling me away. Okay, so what do I feel from this positive? This positive likes repel, and now it's going to make me go that way, and again, size 1, same distance away. Now I'm twice as far away, so I'm going to have a size 1/4 force. Negative on me, so it's an attractive force in this case, 1/4. So the total here, well, that's canceling with that. The total here is 1/4. And 2 1/4 up for A. Let's try C. So what does this positive do to me? Well, it's going to repel me with a size 1 away. What's this negative going to do? It's going to attract with a size 1/4, and that positive on me is going to be a repel again. 1, 2, 3 unit distances away. It's going to be 1/3 squared. So there's this tiny little force of 1/9 going to the left. Now I have to add it up. Well, okay, so it's going to be 1 plus 1/9 minus 1/4, because that quarter is opposing. And the way I do this one, well, okay, you got to get a common denominator. 1 plus 1/9 minus 1/4. The easiest common denominator I see is 9 times 4, 36. So it's going to be 36/36 plus 1/9 is 4/36 minus 1/4, which is 9/36. It's hard to say. So how much do I have? 36 plus 4 is 40. 40 minus 9 is 31. So this one, the net force on this positive is 31/36. That's a hard one. All right, let's hope D is easier. Oh yeah, I like this. So I'm positive. What do I feel from this negative? It's going to attract me with a size 1. What do I feel from this negative? Attract with a size 1. And this, 2 times far away, it's going to attract with a size 1/4. The ones will cancel. It's the same thing as that. And it's a 1/4. Okay, so what would the ranking be? I want to rank these 4 situations based on the net force. So the biggest is clearly A. So my ranking would be A, and that's going to be bigger than C. That's going to be the next biggest. And then I've got B and D equal, and those are the smallest. So the answer for this that I'd be looking for is A bigger than C, bigger than B, which is equal to D. And again, you need to tell me that's equal. Otherwise, how am I to know that you recognize that they're equal? The point of assessments is proving to me that you know what you're talking about. If you make small mistakes, I can't be certain that you know what you're talking about. So make sure anytime there's equal, you show me that it's equal. All right, so that's the second type of problem that we're going to deal with. And I think I'm going to do the next 2 types in a different video. So good job on those 2. Stay tuned. We will continue this practice session. I don't know. I'll do this in another video. So there's 2 more coming up. Good.